the real-time perspective. So if we see about the primary batteries, in a primary battery, the reaction occurs only once, and after the use over a period of time, the battery becomes dead and cannot be reused again. The most familiar example of this type is the dry cell known as Leclanche cell after its discoverer, Leclanche, so which is commonly used in our transistors and clocks. So let us discuss about battery and its history. While dissecting a frog in the year of 1786, the Italian researcher Galvani noted that when his scalpel touched the leg muscle, so it gets contracted from an electric current produced. Later, Volta believed the current was produced by the metal instruments. So the animal, being only a conductor, to prove it, he stamped discs of zinc and copper, which has been connected by conductors and fabric and impregnated by an acid solution. And also in the year of 1800, the electric battery was said to be born. So let us see how this battery works. So here we go. We have a zinc and copper electrode. So a useful galvanic cell can be constructed using zinc and copper. The anode is a zinc bar placed into the zinc sulfate solution. This one is the zinc sulfate solution and this one is the zinc. Which you can able to see it here. So the zinc acts as an anode and here you can see the copper acting as cathode. So let's proceed with the reaction. So this electrolytic solution contains Zn2 plus ions. The cathode is a copper bar placed into a copper 2 sulfate solution, which contains Cu2 plus and SO3. So the two solutions are connected by a porous sodium chloride salt bridge that prevents the two solutions from mixing but allows ions to migrate. So this is the salt bridge. So because of this, if a light bulb is connected, it glows. Attaching a cell shows that the electrons flow from zinc to copper. You can see the flow of electrons from this side, which is zinc, and by this side copper. The reason is zinc is more active metal than copper, so it is more likely to lose electrons. For this reason, the zinc bar is oxidized, producing a zinc ion and 2 electrons per zinc atom. You can see the reaction over here. Zn2 plus ions and 2 electrons. So the copper ions in solution gain 2 electrons and are reduced to copper metal. As the reaction continues, excess positive zinc ions build up in the zinc solution. At the same time, the loss of copper ions from the copper sulfate solution creates an excess of negative sulfate ions. This is how it goes on. So you can see it here. So the positive sodium ions migrate into the copper sulfate solution from the salt bridge. So this is the salt bridge. This one. While the negative chloride ions migrate from the salt bridge to the zinc solution and maintain neutrality of the solution. So the reaction stops when the zinc bar or copper ions are depleted. So the overall cell reaction can be written like, let us see how the cell reaction has been written for a copper and zinc process. So zinc giving zinc 2 plus and 2E minus. In copper, Cu2 plus 2e minus gives copper metal. So here we go with lithium ion batteries and rechargeable batteries. So we have a 6 cells in series in a single strong container that produce a charge of around 100 amps. Enough to throw you off across the room if you happen to touch each terminal. So these are the 6 cells. In each cell, the positive electrode is made up of several connected plates. Each plate is a grid of lead coated with lead 4 oxide. So the negative electrode consists of several lead plates connected together. So you can see it here. Porous separators prevent contact between the negative and positive plates. So the 6 cells are connected in series positive to negative, which you can able to see it here. Everything sits in a solution of sulfuric acid. The plates provide a huge surface area for the reaction. Lithium-ion cells do not use metallic lithium, but lithium ions absorb into the lattice of a graphite electrode. While the cell is discharging, this is anode. Here lithium ions are oxidized to lithium ions, releasing electrons with lithium ions migrating into the liquid electrolyte. So this is how lithium on reaction, this is how it will be, lithium ions plus electrons. So the cathode is usually a metal oxide like cobalt oxide, COO. During discharge, it drags in electrons which then combine with lithium ions from the electrolytes to form a complex precipitate at the cathode. So this is the reaction. Here is the equation for the overall cell reaction. Lithium on reaction is unique in that lithium ions that migrate through the electrolyte. So this makes the cell readily rechargeable. So the lithium ions do not need to be in direct contact with the electrode. Being in the electrolyte is enough for this one. The cell consists of a zinc container that also acts as an anode, and the cathode is a carbon graphite rod surrounded by powdered manganese dioxide and carbon, which you can able to see it over here. So the space between the electrodes is filled by a moist paste of ammonium chloride and zinc chloride. The electrode reactions are complex, but they can be written approximately as follows. Zinc on reaction gives zinc ion plus electron. So you can see here how the commercial dry battery consists of a graphite, that is a carbon, in a zinc container, and the latter acts as a cathode, it's anode. So in terms of a cathode, the reaction will be manganese dioxide on reaction with ammonium or ammonia plus electron gives manganite and ammonia. So in the reaction at cathode, the manganese is reduced from the +4 oxidation state to the +3 oxidation state. Ammonia produced in the reaction forms a complex with Zn2+ to give Zn NH3 2+ ions. So this cell has a potential of nearly 1.5 voltage. So if you see the mercury cell is suitable for low current devices like hearing aids, watches, etc. So this consists of zinc mercury amalgam as anode and a paste of mercury dioxide and carbon as the cathode. Here you can able to see the depiction. So the electrolyte is a paste of potassium hydroxide and zinc oxide. The electrode reactions for the cell are given below. In terms of anode, the reaction will be Zinc amalgam on reaction with hydroxide ions gives zinc oxide plus water plus electron. So in terms of the cathode, it will be mercury to oxide on reaction with water and electron gives mercury plus hydroxide ions. So the overall reaction is represented by zinc amalgam on reaction with mercury to oxide gives zinc oxide plus mercury. So this is how it will be. You can see it here. The cell potential is approximately 1.35 voltage and it remains constant during its life as the overall reaction does not involve any ion in solution whose concentration can change during its lifetime.